In today's lecture, we'll be seeing about multiple linear regression, which is a part of the first unit of Introduction to Machine Learning. So, in multiple linear regression, we can assume we start with the same formula, that is the hypothesis h of x is equal to theta 0 plus theta 1 of x. Now here we have just one feature, that is a single feature. However, in multiple linear regression, we have more than one feature. So in simple linear regression, our data set looks like this, in which we have x as the feature and y as the output. And here we'll have some values. But now in multiple linear regression, we will have a collection of features like x1, x2, and so on up to xn, and a single output or a label. This is for multiple linear regression. So now the formula needs to change accordingly, because here in simple linear regression, we are mentioning just a single feature. Hence, now the formula becomes so here we can have n number of features using this formula, where let us assume that n is total number of features and m is number of training examples. So in this particular situation, if there are n training examples, then we can use this particular formula for the hypothesis. Now, let us see certain conventions. That means when we have xi, now this I is not an exponent, it is just indication that this is the feature vector of the ith training example. Now, we do not have feature as a single value because, as mentioned earlier, so these particular set of features will be considered as a vector. So here, if we have the values like A, B, C, D, E, and the output say Z, then the feature vector x of I represents what? It is a list or a single dimensional matrix, we can say, called as vector, which is a collection of A, B, C, D, E. Here, the value of I will be, suppose, 1. So when I is equal to 1, this is the first feature vector. Similarly, when I is equal to 2, we'll have another vector like. So when I is equal to 2, x of I will represent the vector L, M, N, O, P. So each time x of I will be a collection of all the features. So x of 1 means this one, x of 2 means this one, and so on up till x raised to m. Because we know that we have m training examples. Like this, I equal to 1, 2, 3, 4, and so on, will go up to I equal to m. Because in total, we have m training examples. So suppose I write x of I, and I put one subscript j over here. This means that in the feature vector, x of I, j is a particular feature within that feature vector. For example, x of 1, and suppose I write the subscript 0. This means that in the feature vector x of 1, which consists of the values a, b, c, d, and e, when I write 0, it indicates a. Suppose I write x of 1 subscript 1, then it will represent b. Similarly, x of 1 subscript 2 will represent c. Okay, so x of I represents the feature vector, complete feature vector, and x of I of j represents a particular feature in that feature vector. Now, let us see the cost function. We know that let us take an example before that. Suppose we want to perform house price prediction. What can be the features to determine the price of the house? Suppose feature 1 is in the feature vector, any feature vector x of I, we can have the features like basic house price. After basic price, we can have price dependent on the area of the house. Then we can have price for the number of rooms. Then the price also depends on maybe how long back the house was built. That means age of the house, and so on. So we cannot say that the house price depends on only the area or only the rooms and so on. It depends on a collection of all the values present in this vector. Okay, now let us see the cost function. So for simple linear regression, we had the cost function j, which was a function of theta 0 and theta 1. It was equal to 1 upon 2m summation I is equal to 0 to m of h of x I minus 1 square. For simple linear regression, we had just one particular feature. So if we have number of training examples, we have a single feature, which can be x1, next feature can be x2, next feature can be x3, and correspondingly, we will have the labels. This was the case of the data set in simple linear regression. That is why we are writing x of I, that means x of 1, x of 2, x of 3. And similarly, y of 1, y of 2, y of 3. But in multiple linear regression, our cost function is a function of all the parameters. It is a function of all the parameters, and hence we need to perform the solution execution for all these parameters. Hence, if we compare the cost function of multiple linear regression will also have same formula. But here we know that h of x is what? Here h of x is theta 0 plus theta 1 x. And here h of x is nothing but theta 0 plus theta 1 x1 plus theta 2 x2 and so on up to theta n xn. So this is the difference. Now this was the difference between cost function. Let us consider the difference between the gradient descent algorithm. In gradient descent algorithm, for simple linear regression and for multiple linear regression. So in simple linear regression, we need to repeat certain steps for theta of j, which is equal to theta of j minus alpha of 1 by m summation of I is from 1 to m h of x minus 1. Here, we need to repeat these steps and update theta simultaneously. Here, j can take which values? 0 and 1. Now we need to perform simultaneous update. That means we'll use temporary variables t0 and t1. We'll compute them and then by the same formula, and then we'll assign the values of t0 to theta 0 and t1 to theta 1. In multiple linear regression, again we'll have to repeat the same thing. Theta j is equal to theta j minus alpha 1 by m summation of I from 1 to m h of x I. Let me write it clearly. Minus alpha 1 by m summation of I equal to 1 to m h of x I, where x is nothing but feature vector. And here the x is nothing but a particular value, a single value. Here x is feature vector minus y of. So remember, feature becomes feature vector in multiple linear regression, and the output label will remain a single value in both the cases. Again, let us see the formula in a little more detailed manner. Here we will repeat theta 0 from 1 from 1 to n. So this is the gradient descent algorithm for simple linear regression. Now for multiple linear regression, what we need to do is we'll write the same formula but for multiple theta. So I'll just write that down now. Hence you can see that for multiple linear regression, we again have theta 0 equal to the same formula, and from theta 1 onwards, we'll again have it, and we need to multiply x of I again. We will multiply x of I. Because here we don't have multiplication of x of I, here we have it. And then from theta 1 onwards, in multiple linear regression, we'll have to multiply. Okay, so each time we write for theta j, which is not equal to 0. If j is not 0, we need to keep multiplying x of I. Okay, so this is how it will work. And we can also perform a kind of understanding over here that the theta 0 over here corresponds to the theta 0 over here. The theta 1 over here corresponds to the theta 1 over here. And then we have some additional features. Okay, Now, for simplification purpose, what is our normal hypothesis function? H of x is equal to theta 0 plus theta 1 x1 plus theta 2 x2 plus theta n x2. For simplicity, since each one has a particular variable multiplied to it, each time a variable is multiplied with the corresponding parameter or coefficient. These thetas are called as parameters, and these features these are the features. Okay, so for simplicity, what we'll do is we will write an x0 over here. We'll multiply x0 with theta 0. And always remember x0 is always equal to 1. Why x0 should always be 1? Because whenever we multiply 1 with anything, we get the same number. A into 1 will remain as A only. Initially, what we had theta 0. Hence, to keep it as theta 0, and just for convenience purpose, we need to multiply 1 with it so that we get theta 0 with 1, which is nothing but theta 0 only. So this is how we can do it. Now, this is because we want to express the things in the form of matrices. See, now if we write h of x, we will write it as theta 0, x0 plus theta 1, x1, and so on up to theta n, xn. Now, if we want to represent this in the form of a matrix, how we will write it is, let us consider theta is a vector. Vector is nothing but single dimensional matrix. Single dimensional in the sense either number of rows will be 1 or number of columns will be 1. So suppose we have considered only 3 parameters. In such a case, theta is a vector of theta 0, theta 1, theta 2. And the size of this particular structure is nothing but number of rows are 3 and number of columns is 1. Number of rows is 3 and number of columns is 1. So these are the rows, first row, second row, third row, and this is the single column. Similarly, our feature vector x can be represented as x0, x1, x2. This is also 3 cross 1. So if we perform matrix multiplication of theta transpose with x, what will we get? Now theta transpose means the rows become the columns and columns become rows. So theta transpose is nothing but, now there's a single column which will become a single row. And now the size has become 1 row, 3 columns. I hope you understand this basic calculations done in matrices. So theta transpose into x will be nothing but theta transpose, theta 0, theta 1, theta 2 into x. That is x0, x1, x2. So when we multiply this, how do we do the multiplication? We take first row multiplied by first column and we'll keep adding the products. For example, if you know about this, you will say that the answer will be take theta 0 with x0 and multiply. Plus take theta 1 with x1 and multiply. Plus take theta 2 with x2 and multiply. So on performing the matrix multiplication between theta transpose and feature vector x, we will get this particular answer, which is nothing but our linear equation. So that is why for matrix multiplication simplicity, we are going to write an x0 over here multiplied with theta 0. Right? Or you can also, instead of x0 over here, you can directly put the value as 1. That is the idea behind this. Now let us consider a particular example in which we'll see that how we can avoid multiple features also. Suppose we have the features of a house. Suppose this is a house. Then we have a particular front area. So this is called as frontage, the front area of the house. And this is called the depth or the breadth. Basically, frontage is nothing but length, and depth can be assumed as breadth. So area of this particular house will be nothing but frontage into depth. So if we want to express the calculation of area as the hypothesis, suppose we want to consider house price prediction only. Suppose we consider house price prediction in which the price has to be predicted, which is the hypothesis. We can express it as theta 0, which will be constant, plus theta 1 x1 plus theta 2 x2, where x1 is the feature called as frontage and x2 is the feature called as depth. However, if we want to reduce the number of features and parameters, if we want to reduce this to a single product, then what we can do is, we know that area is equal to frontage into depth. So why not add another feature in our data set? So till now, our data set was like this. We had frontage, we had depth, and then we had the price. Now we'll eliminate two columns or two features and make this as a single feature. So we are combining two features into a single feature using the area is equal to frontage into depth formula. And now what the hypothesis will become? Now the hypothesis will become h of x is equal to theta 0 plus theta 1 x, where x is nothing but area. So this is how you can reduce the number of features if you want to reduce the complexity of the program. So this was about multiple linear regression. We'll also execute a program and check our understanding. So here, this is a machine learning example of linear regression with multiple variables. So the sample problem is to predict the home price located in New Jersey. So here we'll import the libraries, pandas as PD, numpy as NP, and from sklearn we'll import linear model. Why do we need this? We have seen in our practical execution of linear regression with one variable. We know that sklearn dot linear model. From this we import the class called as linear regression. Hence we need this particular thing. And import matplotlib.pyplot as PLT, or instead of writing it as an import statement, we can also write percentage matplot inline matplotlib. Instead of writing import for this particular matplotlib.pyplot, we can write percent matplotlib inline as well. Now we have the data set, this one, in which we have three features: area, bedrooms, age of the house, that is x1, x2, x3 feature vectors, and then the price y, where x1 consists of all these values, x2 consists of all these values, and x3 will consist of all these values, and y is this one. So if we see df dot shape, it indicates that how many rows, how many columns. We can see that there are 6 rows and 4 columns. Now we can also find the median. How do we do that? df dot bedrooms of median. Now if we want to access a particular feature vector, that is a particular column, like suppose this entire column or entire feature vector we want to access, or maybe this entire one, then what do? We can either write it as df of within quotes area. So if you print this particular value, you'll get this entire area column. Or instead of writing it this way, you can also write df of within double quotes area. Or if you want to use another way, you can write df dot area. So df dot bedrooms, we can write dot feature name also instead of using the square brackets. And keep in mind, the names of these columns are case sensitive. That means AREA is not equal to capital AREA, or AREA is not equal to small a capital REA. Okay, these are case sensitive, so these are not equal. Now we need to extract the feature separately and store it in X, and extract the label separately and store it in Y for our processing. So what we'll do is our data set consists of area, the number of bedrooms, and the age. And our output is the price. So we want only these to get stored in a data frame called as X. This is a 2D structure called as data frame. So in order to extract this, what we have to do is, from our original data frame, you drop the price column. Drop means you eliminate the price column. Okay. So when you do df.drop, column name and access is equal to columns means it will try to find this price identifier or the price variable in the columns. Means in the columns it will first check, is this column name equal to price? No. Is this column name equal to price? No. Is this column name equal to price? No. Is this column equal to price? Yes. Then it will drop this column. And this dropping will happen temporarily. So again, after dropping, whatever is the result, that means area, bedrooms, age will get stored in X. Now if you print df, what will you get? All. You'll get area also, you'll get bedroom also, age also, and price also. All will be there, because this updation of deletion that you have done, of dropping that you have done, is temporary and it has not been done on the original data frame. Suppose this deletion or updation you want to do permanently on the original data frame, then you need to pass an additional parameter, put a comma, and you can write in place equal to true. That means in place of the original data frame, the deletion will be done. However, we don't want to update the original data frame, suppose as in this case, then we will not write in place is equal to true. That means by default in place is equal to false, which we are not mentioning. And then y is equal to a single column, that is the price column that we are storing. So now X consists of all the features and Y consists of only the price label column. So you can print X and Y. And then what we'll do is, you need to plot the graphs of each feature against the label. So what we will do is, you extract a single feature. Now remember, always a single feature versus the always a single feature versus the label is done. You cannot have x1, x2, x3, all of them on the x-axis. No. At a time, you can take only x1, only x2, or only x3 and plot it against the output y. So suppose you take only x1. Suppose you take only x1 on the x-axis and y on the y-axis. Then you will consider, suppose x is 1, then y is suppose 2. You'll get 1 point. Suppose x1 is 3, y is suppose 4. You'll get 1 more point. And this way you will join these dots wherever you get the dots and you'll get this particular graph. Now, why is the relationship not linear between them? Because the price y does not only depend on x1. No, price y depends on x1 also, x2 also, x3 also. So there may be certain differences that for if the area is less, suppose area is 3 square meter, then suppose price is 5. Then in the next case, area is suppose 2 square meter, but price is 6. But if area is lesser, price should also become less. But this does not happen because price depends on other features also. Though the area is less, maybe number of bedrooms are more. Maybe number of bedrooms is 1 only over here, and number of bedrooms is suppose 4 over here, and number of bedrooms is only 1 over here. So 3 is the area with 1 bedroom, 2 is the area with 4 bedrooms. So definitely here the price will increase. That means your price does not depend on a single feature. That is what I want to say. So we can plot the graph of now bedrooms versus price. Here you can see some different kind of graph. As I mentioned, because total dependency is not on a single feature, you get such kind of graphs. So scatter is the function by which you can get these points, which are highlighted, and plot this feature and this label means the line will get drawn passing through these data points. And then what is the label for the x-axis? Label means what is on the x-axis? Bedrooms. And what is on the y-axis? Y label is price. Similarly for age against price. Now import the linear, first you have to split the model, split the data set. So again, from sklearn.model selection, import train test split. This is a function. You pass the parameters, features. Now, I always told you that whatever feature you're passing, it is always in 2D. That means you can say that it is a data frame in itself. And we know that, yes, this, which is the features X, is a data frame. So it is always in 2D. That is why even if we have a single feature, you need to pass it as a 2D structure. So whenever you have a single feature, it should be like you have only area and here you have indices, suppose. So this should be a data frame which has a single feature. So now you're passing the feature, you're passing the label, test size. That means you want to take 20% out of all the training examples, out of all the examples in the data set, you want to take only 20% for testing. That means remaining 80% you will take for training. And random state I've already explained in my previous video that we are setting. So here we have split our data into training, testing. Similarly, the label also for training, testing. Then we'll build the model, we'll fit it. We have the coefficient, we have the intercept, and based on that, we'll predict, and then we'll compare. Same steps as the previous video. And then we can predict for a custom input from the user. Then we'll see the remaining part in the next lecture due to restriction on time. Thank you for giving me a patient listening. So in the previous lecture, we were seeing the execution of a program related to multiple linear regression or multivariate linear regression. So here we were at this particular stage in which we had imported the train test split function, and then we passed the features, that is the set of feature vectors actually, and is the label with test size of 20%, that means 80% for training and random state 0. Now this is the training, x train, x test, y train and y test. Then we create an object of the linear regression class, and then we'll fit our model by passing the training feature vectors and training label. So we'll get a coefficient array this time, not a single coefficient. Why? Because in simple linear regression, we know that our hypothesis or the best fit line can be given by theta 1 x plus theta 0, where this is the y-intercept and this is the slope. And both are called as parameters. But in multiple linear regression, we know that h of x is equal to theta 1 x1 plus theta 2 x2 plus theta 3 x3 plus theta 0. Why I'm taking up to theta 3 x3? Because here we know that we have three feature vectors. So theta 1 stands for area, theta 2 stands for number of bedrooms, and theta 3 stands for age of the house. Okay, so here we have these three parameters. So we know that the coefficients that we have will be these four, and the intercept is this one. So we know that theta 0 is the intercept. So intercept is a single theta 0, which is equal to this value. And our remaining coefficients are theta 1, theta 2, and theta 3. These three are the coefficients. Hence, we have y pred, in which we will predict based on the testing features. Now we know that x test consists of feature vector area, feature vector bedrooms, and feature vector age. So we have this one set and this is the second set. We have two sets of values. So first and second. Now, since we have two sets of values, we will get two predictions. So for set 1, we have the area, the bedrooms, the age, and some price out. Again for set 2, we have some area, some bedrooms, some age, and again price. So here for set 1, the output price is this one, and for set 2, the output price is this one. And then we can have a comparison between the actual value, that means y test, and the predicted value y pred. Similarly, we know that for testing the features, what we are given is in 2D, we have passed 1, 2, 3 values, that is area, bedrooms, and age. So similarly, here in 2D, we are specifying this particular set, for which we will get some output on prediction. If you print the value of y, which is equal to this, we will get the predicted price for this particular set of features. Now, we know that we have found out theta 0, theta 1, theta 2. These are our theta 0, theta 1, theta 2. So this is, we know that in simple linear regression, h of x is equal to what? Theta 1x1 plus theta 0, theta 1 x. This is theta 1 x. But in multiple linear regression, if we have three particular feature vectors, then h of x is equal to theta 1 x1 plus theta 2 x2 plus theta 3 x3 plus theta 0. Now, this x1 is a value coming from the area feature vector. This particular x2 is a value coming from the number of bedrooms feature vector, and x3 is a value coming from the area feature age feature vector. So, and theta 0 is a y-intercept. So we know that we can predict for, when we are predicting, we need to pass x1, x2 and x3. Now what will be the equation of the line y? This is the line. So the equation of the line is, see here, this over here, this is theta 1 into x1. This is theta 2 into x2. This is theta 3 into x3. And this is theta 0. Okay. Why can I say that this is only theta 0? Because I can see there is no multiplication term along with this. We have a product over here. Means it is theta into feature. Here also product theta into feature. Theta into feature. This is only theta. That is y-intercept. So this is how we can have multiple linear regression. And next we will see what is polynomial regression. If we talk about a linear function, we can say h of x is equal to theta 0 plus theta 1. If we talk about quadratic function, then h of x is equal to theta 0 plus theta 1x plus theta 2x. Suppose we talk about cubic function, then we have h of x equal to theta 0 plus theta 1x plus theta 2x squared plus theta 3x squared. Right? Where x is a feature. Suppose we have this as our data set in which we have x and y as feature and label. Then this particular thing is our feature. X square will be the square of the feature and x cube would be cube of the feature. Right? Now, if we go for such functions or equations, for linear functions, the graph will be a straight line, either it will be constant, or we can have a graph with positive slope or a graph with negative slope. This is for linear. For quadratic, what happens is, for quadratic, the graph comes out to be like a parabola. It will go on increasing exponentially, and then finally it will go decreasing. Suppose we talk about cubic, then cubic also has a kind of curve, but it will never go down. It will increase and then somehow it will rise exponentially. It will not come down. Okay. Now, involving squares and cubes in our function is increasing the complexity of computation. Hence, if we consider the square or the quadratic function, we can reduce it further by writing it as theta 0 plus theta 1x plus theta 2x. What I have done is, instead of x, I'll take square root of x, and instead of x square, I will take x. Right? So, we are converting it into a square root function. And we know that the square root function also has an increasing graph, somewhat like this, and it will be this way. That means it will not come down. For square root function, the graph will be this way. So once again, for linear function, it may be constant or positive slope or negative slope. For quadratic, we have something like this and it will go this way. This is for x. This is for x squared. For x cube. If we consider x cube, then graph is somewhat like this. If we consider square root function, then the graph will be somewhat like this. Hence, we can prefer the equations in which the powers are not square or cube. This is how we can implement polynomial regression as well. So the basic idea is following a hypothesis function in which we have parameters and parameters along with product of features and so on. So this was all about linear regression. We have seen linear regression, which is a part of supervised machine learning. In linear regression, we have seen simple and multiple, in which we have single feature and single label, or we have multiple features and single label. So this is how we have seen linear regression. And then we know that in linear regression, we need to minimize the error, which is the difference between predicted y and actual y for every sample example. And this is represented by cost function. And in order to reduce the cost of the error, that is to optimally select the parameters theta of j, where j can be from 0 to n. In order to select the appropriate theta, what do? We use gradient descent algorithm, in which it is an iterative process. And from this, we can understand that how we can reduce the cost in a linear regression. So this is it for linear regression. I hope this topic is clear. Thank you for giving me a patient listen.